Hi, everyone. Think it is time to start the presentation and the workshop for today. My name is Sina Tagavikish. I am project manager with OGC. I will just go through a very brief presentation here. It doesn't have really much, just the agenda and what we have for today. So thank you for joining today's presentations from wherever in the planet that you are joining. I hope you will enjoy it. It's actually a 2-day event. So the AI-DGGS workshop has 2 days of planning for the upcoming basically presentations and discussions. The day one is going to be more of basically more of a presentation kind of format. So not going to be too much time for the Q&A, but fear not, we're going to capture all this discussions or your questions for today if we cannot actually answer those. So just going to ask you an administrative request to mute yourself and let the participants and the presenters and the sponsors present their talks and discussions. If you have questions, we will have time for it, but definitely put them in the chat. We will look into them, and if the presentations allows, maybe we will have some time during the presentations as well, but that depends to the presenters. So that depends on our timing as well. For agenda for today, we gonna have some introductions from the sponsors. If they are here, they will give a very short talk. The whole idea is that we wrap up that introduction in 10 minutes. And then our ER editor, Stelios from Hartis, will provide a 10-minute general context about the pilot. Then each of our participants start presenting their results. Each one will have 10 minutes, and we will have a break at exactly 1 hour and 40 minutes. So we will have some like a very short break, 5 minutes or so. And again, depends on how fast we can move forward and how slow we can go. Maybe we can add 5 more minutes to the break. And the last piece of today's event gonna be a wrap up and QA. But tomorrow, we will have 3 panels that will go through details for your questions or your concerns or whatever you have. So we will look forward for you to join us tomorrow as well. And so just to tell you how we did this, the pairing is based the list that you saw is actually based on the architecture of the pilot. So we start with the servers that provide DGGS services, and for each of the servers we have ties with clients. So each client comes after all the servers that are tied into. So the client at the end will have the most ties basically with the rest of the servers, but that really does not mean much because we have done a lot of stuff that you will see today. And we did this so you will hopefully enjoy these presentations. And with that, I just want to mention and thank the OGC team, Dr. Ingo Simones, our Chief Technology Officer. He actually was the main force in the OGC to push for this, and I was just helping out, trying to manage this pilot, kind of a cat herding, because we have too many participants. And with that, I would like to thank our sponsors, Natural Resources Canada, United States Geological Surveys, ESA, European Space Agency, and CNES Center National to this Specialis, which is the CNES, the French space agency. So with that, I would like to ask Ryan Ahola if he's available to unmute himself and introduce himself and take the scene away.
Okay, great. No, thanks, Sina. Yeah, so my name's Ryan Ahola. I'm a geospatial scientist with Natural Resources Canada. So we're one of the groups, as Sina mentioned, that sponsor this work. So I'd just like to give a few minutes of remarks just to talk about our motivations for this work and why we participated in it. So our program here at Natural Resources Canada, we focus on spatial data infrastructure and trying to improve interoperability of geospatial information. So essentially making it easier to find, access, share, and use. Over the last few years, we've been working a lot more closely with the emergency management community in Canada and trying to understand their needs and requirements for use of geospatial information interoperability. And what we've learned from working with them is that there's a strong interest in using geospatial a lot more and using it in an interoperable fashion, given the number of stakeholders that are involved in emergency management across the country. And they're interested in new ways of using geospatial information. So this work with integrating artificial intelligence into discrete global grid systems with a lot of different types of geospatial information is a really good opportunity to explore that. And our initial motivation for this work was really to see how discrete global grid systems in combination with AI could support different types of emergency management needs in an interoperable way through OGC standards. So this is things like being able to prepare for emergencies, respond to them when they're occurring, and then help to recover from them after they're complete. And there's an interest in both present-day emergencies, so working with like helping to support disasters that are happening today, but also planning for future emergencies that will occur years from now under different types of climate change scenarios. So we've been really excited by the work that's been undertaken. All the participants have done an amazing job, so we're really excited to be participating in the workshop today, and we hope that you all are interested and benefit a lot from the material that's presented. So with that, I'll just say, to say thank you to Sina and Ingo and everyone else at OGC who's helped with this work. It's been really well organized and well executed, so we're really appreciative of that. Thank you also to all of the other sponsors, USGS, ESA, and CNES. For your funding. And lastly, thank you to all the participants for your excellent work and for being here today to showcase what you've done. Yeah, so with that, I'll pass it back to you, Sina, to continue. Thank you.
Thank you, Ryan. I see Salvatore in the call. Salvatore, do you want to unmute yourself and maybe show your screen and maybe talk for a very short and brief introduction?
Yes, thank you. Can you hear me well, by the way?
Yes,
Okay.
very well.
Thank you. So, I'm Salvatore Pinto. For who does not know me, I work in the AI and data science section in the technology department in ITA, and I also support the Earth observation program in several activities, one of which is all the activities related to standardization, also involving the OGC, etc. I have to say we were very happy about the opportunity to sponsor this, let's say, this activity, also because my section, but overall LISA is facing, of course, a lot of AI and AI-related projects where we see that standardization is very, very relevant in the realm of sharing models, sharing application, etc. And also DGGS is a quite important topic for us. Both in the way we, let's say, distribute the data, but more in how we can make it more accessible to our community and more easy to be used, for example, for AI or other contexts. So these, let's say, the topics which were proposed here resonated quite a bit with our internal interest and strategy. Of course, we let's say retrieval-augmented AI, which is what is in the topic here, was and it still is part of our strategy. And disaster management, as an example, is a field on which ESA is very active with the charter initiatives and other initiatives. So just to say, all of this is very relevant to us. We are thus very happy to see the results and all the work that you said, and for sure we will analyze these results and take them into consideration for the future activities that we will do in the agency. So thank you a lot to all. Thank you a lot to NRCan for being let's say very active, and USGS also in the definition and the conduction of this, and to the OGC for having proposed this, and obviously to everyone who did the hard work here. So thank you a lot, and I'm looking forward now to see the results.
Thank you, Salvatore. I appreciate that. I don't see Rich Fraser on the call, so I guess whenever he joins, or he might not be able to join, he will give a very short talk. But let's delve into the presentations. And the first presentation for today is Ichere. So I will ask Jerome to take the scene and introduce himself. Actually, Stelios, sorry. Yes, Stelios to Hartis. So Stelios to actually is our ER editor. So he will give a background about what we have done. And let's start. Okay.
Thank you, Sina. Can you hear me well?
Yes, very well.
Can you see the presentation?
Yes, yes.
All right. Thank you, everybody. My name is Stelios Kontarinis. I'm from Hartis. We are based in Athens. It's a rainy day today, and the schools are closed because of the heavy rain. That's a bit strange for us. Let's delve into the project, and I will take you some of the main ideas of the project and why we did it, and until where we have reached. The project in a nutshell, our motto is one digital fabric and instant answers. The pilot successfully demonstrated a breakthrough in disaster response, giving artificial intelligence a geospatial brain. By unifying global data standards, we proved that AI can now interpret a crisis as easily as it can interpret a text. What was the challenge? The fragmented ground truth. In a crisis, decision makers are buried in data, but starved for information. Satellite imagery, flood models, and infrastructure maps speak different languages. The pilot addressed the discovery gap, where the barrier that prevents responders from getting instant answers to plain language questions. And what is the innovation? A universal language. We created a digital fabric with discrete global grid systems, a global grid that aligns pieces of data perfectly, one above the other. Then we orchestrated with AI how to read the data. We enabled 4 independent AI clients and 6 DGGS data servers to work as a single interoperable engine. And what is the future? The future is decision makers can now use plain language queries to answer questions about disasters, like identifying high-risk zones for flooding. The pilot successfully unified geospatial data for the Red River Basin in Canada, demonstrating how DGGS and AI can enable more resilient emergency response. The journey started early in May 2025. The kickoff of the project was in mid-July, and now we are happy to present the results of the pilot by the end of January. It is a OGC Collaborative Solutions and Innovation Program initiative and sponsored by the organization that already presented. Let's deep a bit more into the details. What is the problem that we are trying to achieve? It's emergencies are increasing in frequency and damages are escalating. There are huge data sets of information or geospatial information that needs to be managed in emergencies. And there are multiple challenges there: complex analysis and utilization, sourcing data from many providers, diverse management stages, and exploring new approaches is required. Can DGGS help on that? Well, as said, emergency management software lacks intuitive AI interfaces that allow non-experts to ask complex questions about geospatial data. And the current geospatial standards were not designed for chat to map AI interaction or non-congruent grid interoperability. The experiment is that DGGS divides the Earth into fixed area cells, often hexagons, as a spatial tokenizer or spreadsheet of the Earth, and this allows disparate data to be integrated into a single cell structure, which AI models can analyze more easily than traditional coordinates. Let's see a couple of research questions. In terms of LLMs, can LLMs accurately query geospatial APIs without hallucinating coordinates? In terms of interoperability, can OGC standards mediate data exchange between independent grid designs? Is DGGS effective for harmonizing diverse raster, vector, and temporal datasets? Can AI agents automate complex geospatial workflows, analysis and visualization within the grid? What specific updates are required to make OGC DGGS standard AI ready? The goals of the pilot is to demonstrate how systems using different DGGS grid designs can use the OGC standards to exchange spatial and temporal disaster data and related information. Explore how DGGS systems can be enhanced with standard-based AI ML tools, natural language queries, AI-driven insights, and automated analysis and pattern detection. Provide accurate, authoritative, hallucination-free responses. The focus is always on exploring emergency management capabilities, having a single view for understanding what is happening to support disaster decision making. The standard can support integration analysis, visualization needs of emergency managers, current and future emergency management contexts, testing DGGS approaches and operability through a flooding scenario in Manitoba, indicators to inform decision-making for mitigation and response, exploring integration of AI approaches to make DGGS intuitive and accessible for users like emergency response coordinators. Why DGGS? Traditional GIS systems are rooted in legacy of paper maps and navigation. To make flat maps from around Earth, we use projected coordinate systems, but this comes with a cost: distortion of shapes, areas, distances, directions, depending on the projection. The image illustrates the distortions presented in the conventional Lambert projection, where compared to how it should be displayed using hexagons of the same size. In the polar regions, we see the size of the hexagons appears exaggerated, while they remain relatively similar in the equatorial regions. DGGS takes a modern digital-first approach, represents the Earth not as a flat map, but as a spheroid divided into hierarchical uniform cells, enables accurate, scalable, and resolution-consistent geospatial analysis, perfect for today's global digital workflows. DGGS results in compatible formats, projections, and resolutions. It enables quick search and query. Integration is complicated between raster, like satellite imagery, and vector data roads layer. Both raster and vector can be depicted in the same hexagonal cell format, simplifying analysis and integration. There has been a decade of DGGS in OGC from the first standard, the first edition of the abstract in 2015, the testbed 16 in 2020, and the latest pilots, the FMSDI Phase 3 RTSDI, the FMSDI 5, the start of this pilot, and the standard that was published in late 2025. What is the scenario for this pilot? All work is anchored on a specific hypothetical disaster scenario where the location is the Red River Basin in Manitoba, Canada, specifically south of Winnipeg. A major flood event modeled after the historical floods either of 2011 or 2020 caused by record snowfall and severe weather. To provide emergency response coordinators with a common operating picture, the need is to ask natural language questions, identify neighborhoods that will likely be impacted by flooding, and receive accurate data-driven visualizations and answers. We used an integrated mix of static and dynamic datasets like RCM Radarsat data, historical national air photo library imagery, weather JEPS data, ERA5 data, terrain like Canadian digital elevation model and LiDAR data, infrastructure from OpenStreetMap, and world population density. What is the operability workflow? The pilot is structured out of having both servers with a naming of D100 acting as dataset endpoints and the clients that consume this data from the servers. In order to have the interoperability experiments, the clients are supposed to get data from multiple data servers, and multiple clients utilize and servers facilitate multiple clients. Several grids DGRSs were tested, like IZEA 3H, IZEA 7H, IZEA IG07, which is the IZEA 7H using the Z7 indexing system. Arhelpix, Gnosis, Global Grid, A5, H3, S2. We see on the slide the different apertures on various DGSs from aperture 3, aperture 4, and aperture 7. On the AI client architecture, what we mainly tested, it's testing heavily the RAG, the Retrieval Augmented Generation, which is the context engine. It helps us making the ground truth, connect the AI to authoritative DGGS data, preventing hallucinations by forcing answers to be passed on retrieved facts, like specific flood models. Allows AI to query live data endpoints rather than relying on stale training data, essentially for real-time disaster response, and delivers domain-specific expertise without the massive cost and time of fine-tuning models. And the main work was done through MCP, the Model Context Protocol, which is the action protocol. It provides a universal way for AI agents to read API capabilities and metadata without custom coding for each server. Enables the AI to plan and execute multi-step workflows, find the flood zone, query the population, report impact by treating API endpoints as executable tools, and connects the static reasoning of an LLM to dynamic real-world data streams. I think I have very few minutes. I will. Okay, we have seen the sponsors. It's NRCan, ESA, USGS, CNES. The participants who provided a server API, AOGC API, DGGS server implementation, it's the GeoLinks, Akere, Geomatis, CRIM, GeoInsight Safe Software. The clients were from Hartis, CS Group, CompuSol, TerraFrame, and the common operating picture was from 4113 Engineering. I will not go into details. I've seen the time have passed, so we will discuss about them tomorrow, where we'll wrap up what we have seen today. I think we have seen this. This is another way of seeing the architecture that we have. From one side, the server backbone, and from the other side, the agentic AI analysts, and the COP is the glue between them. For the COP, Lucio will have a detailed presentation today. It's about moving from static maps to machine-readable JSON schema, extending the OGC web services context It's an old standard that serves as a structured knowledge context for both human operators and AI agents. And okay, one slide for the pilot achievements. It's a brief one. We'll talk more about it when we will wrap up the presentations of today, tomorrow. Regarding interoperability and data, we validated DGGS as a unifying fabric to merge heterogeneous data across independent server-client implementations. We successfully exchanged data across distinct grid structures, bridging the gap between raster and vector datasets, implemented RAG and MCP to ground large language models with authoritative OGC API data, delivered functional chat-to-map interfaces where agents chain API calls to interpret user queries. And regarding standardization, we leverage iterative reporting to capture technical friction points, resulting in a gap analysis report section that recommends concrete updates to OGC standards. And commitment to maintain all this work that we have done for 12 months to facilitate ongoing ISO OGC review and stakeholder evaluation. The project website, this is the first page. This is the link that currently is hosted. And this is the menu and the structure of the website. It has the mission, the challenges, the scenario, the architecture, the DGGS frictions, details about AI orchestration, presentation of the participants' works, the servers, the clients, and the section on the OGC roadmap, the partners, and the final report of the pilot. Thank you. Back to you, Sina.
Thank you, Stelios. With no further introduction, let's delve into the first server, Jerome Ichere. Please share your screen and okay. We can't hear you yet, so.
Can you hear me now?
Yes, we can hear you now.
Can you see my screen?
Yes.
Great.
Perfect.
Hi, Jerome Saint-Louis from HRA, and so we were providing an OGC API DGGS service, as well as the foundational discrete global grid abstraction library, or DGGAL. So a few words, well, actually I have a lot of words about the DGGAL, which is really what we mainly focus on during the pilot. So DGGAL provides a common interface for doing several types of operations on multiple discrete global grid reference systems. So instead of having to deal with different libraries to work with different grid systems, you have a uniform API that works the same regardless of which grid you use. So this makes it easier to well, you're not tied to a particular grid, and it's also facilitate the integration of data from one grid to another. So DGGAL is an open source, free and open source software project under the BSD3 license. We have a Python package. Pip install DGGAL is pretty much all you need. And also, if you use QGIS, I recommend you check out the vGrid plugin, which lets you play with DGGAL from the QGIS user interface and explore. So not only the grid that DGGAL supports, also some other grids like A5, for example. So that's a cool thing to try if you haven't already. So what the grid that DGGAL first supported, we started, a lot of this started in the FMSDI phase 3 that was mentioned earlier, where we basically started working with IC3H, which is aperture 3 hexagonal grids. And those grids are truly equal area. So unlike H3, which is the hexagons are not exactly the same area, with the ICEA grid or the IVIA grid that I'll talk about in a second, every hexagon is exactly the same size. And the only exceptions are the 12 pentagons, which are exactly 5/6 the area of the hexagon. And IVIA is this basically, instead of, in the original paper from 1992 from John Schneider, there was this mention that the dodecahedron actually had several advantage over the icosahedron for doing the equal area maps projection based on polyhedral globes. So actually, the dodecahedron is the best choice. But for some reason, everybody has been using the icosahedron. So what you can do is you can simply change the projection. So you don't actually have to change the grid construction at all. So all the work that exists for the ICEA grid can easily be transposed to the IVIA projection instead. And what you get is you avoid these cusps that basically result in less compact or less regular shapes that are further away from a circle. So basically, all the grids that we support for hexagons and for rhombuses in DGGAL, you can choose between IVIA and ICEA. And there's also a third option, which is kind of in between in terms of the nice properties, which is the rhombic triacontahedron equal area projection. So basically, we support, what it is actually, it's just a choice of from which vertex you map great circles to straight lines in the projection. And you have three choices, and those are basically the three options. IVIA is the best choice, but you can choose any of them. So we support the 3H for aperture 3, and we support the rhombic, so which divides in the rhombic aperture 9 divides in 3 by 3. So that's for the equal area icosahedral projection. Then we also support the R-Hill PIX, which is the subdivision there is also 3 by 3, aperture 9. And we also have the Gnosis global grid. And the Gnosis global grid is essentially, it does not involve a projection at all. It's based on a 2D tile matrix set. And your zones are essentially just WGS 84 bounding boxes, which makes it very, very easy to work with. It's also a lot faster because there is no projection involved. And it's also a very good choice to kind of be like the universal adapter to go from data in one grid to another, because you basically unproject into the Gnosis global grid, and then you can reproject into the projection of another grid. So it's kind of a nice choice. So those were kind of the three types of grid that we supported before the project started. And during the project, we a lot of most of the efforts has been on implementing support for new grids. So one grid we added support for was HillPix. Another one was the aperture 4 rhombic. And then the one we put the most effort in was the aperture 7 hexagonal, ICA 7H, IVIA 7H, RTEA 7H. And also one of the things we did was implement so that there is one indexing for 7H, which is described in the OGC API DGGS standard Annex B. And that's the one you see on the left. But you also implemented support for Z7, which is what is part of the IGO7 DGGRS for interoperability with other participants, which were interested to use the Z7 or IGO7. So that's the one you see on the right, which is a hierarchical indexing. And we still want to add support for more grids, so we started to work a little bit to try to implement A5, which is all pentagons. So this with A5, the nice thing is every single zone is exactly the same area. You don't have this special pentagon exception, however small the pentagons are, because you always only have 12 pentagons. So the finer you go in the levels, the less insignificant they become, and they're always also in the water. So if you're working on data on land, the pentagons are not really an issue. But if you really want all your zones to be exactly the same, then there's A5, which is pretty cool. So we've started to implement support for this and some other things like the NUnique indexing for HillPix. So how can you use DGGAL? You can use it in pretty much any programming languages. So C, C++, Python, Rust, Java, JavaScript, in a WebAssembly environment or in Node.js. The library itself is written in our EC programming language, which is native and very high performance, and also is very expressive and has some nice reflection capabilities, which is what enable us to automatically build a lot of these bindings using the reflection that's built into the EC language. Also, Joan will probably talk about this later in his presentation, but he helped us prepare some bindings for Java. So he put together the bindings for Java based on our C bindings. So just a very quick look at everything that the library. So it's a very comprehensive API. So you can query the DGGRS as a whole. You can ask the property of a specific zone. You can convert scale or resolution or reference zone area to a refinement level and vice versa. You can query the topological relationship between two zones. You can, yeah, so this is pretty much all. One special type of topological relationship is whether a zone is a subzone of another. So that's a very important concept. And basically, a zone is a subzone of the other if their interior intersects. Other functionality, there's a functionality for zone compaction, which is the action of replacing a bunch of small zones by one bigger zone that kind of stands for the other smaller zones. Also list the zones within the bounding box, or list the subzones, like I was saying with the topological relationship. Also, given a subzone index, knowing what the zone what the zone is, or vice versa. If you know you want to know what is the index of a subzone into its larger zone. So that's the kind of operation you can do. And then there's geometry operation like querying the centroid, the extent, the vertices, both just the nodes or also vertices along the zone boundaries to get a very precise description of the zone boundary. Other things, of course, is a conversion of text identifiers to 64-bit integer identifiers. So the library is all using 64-bit integer internally, or getting a zone from a point, and yeah, listing the zones within a bounding box. So that's kind of what the API can do. And then we also were providing our Gnosis map server as an implementation of OGC API DGGS for clients to access. And one of the main things we achieved was to integrate DGGAL into it, so that now the Gnosis map server supports all of the DGGRS that DGGAL supports and all the other ones that we'll add to it. Also, our Gnosis map server supports the common query language for both filtering zone data and zone queries. And it supports on-the-fly conversion from one DGGRS to another, effectively requantizing or resampling the data. And another capability that we have is that our basically our OGC API DGGS data access or query access can sit on top of our processing engine, which basically can create virtual collections. So you can describe a workflow that produces a geospatial data collection, and then you can do DGGS queries that will trigger the processing based on which zone you access. So as you zoom in or pan or you progressively evaluate some zones, then that triggers the processing for that region and time of interest. And on the right, you can see here one sample response page from our zone information resource for a particular zone, where you can explore and go through the children and the parents and the neighboring zones with some previews. Another thing we spent a lot of efforts on was to design a scanline-based deterministic order for 7H subzones. So that was part of the implementation of the 7H DGGRS. So some very interesting patterns, how these zones are numbered. You can see from 1 to 11, for example, in the Pentagon here. And these are key to the data encodings, the DGGS JSON and DGGS JSON FG in particular. Another thing we made quite a nice discovery quite late in the pilot about the area under the fractal curve. So when you do a sort of a basic aggregation with the 7H, you kind of the containment is not perfect, so you can take the shortcut of only considering what we call the logical children from the indexing rather than all the actual subzones that intersect. And if you do this, you basically you consider zones that are outside and you miss zones that are inside. And what we did is made some interesting mathematical discovery about how to exactly quantify that value. So there will be more details about this in the ER. And one of the very interesting project we did was some vibe coding, which basically we built a whole DGGS infrastructure around the concept of a DGGS store that is based on the DGGS UBJSON and the DGGS UBJSON FG formats. And just a quick overview of what that looks like. So you can see on the left, we have some directories and SQLite files. And inside those directories, we have more SQLite files. So it's kind of the idea is it's scalable because it can scale to petabytes. There's really no limit because it always basically balance the number of directories with the number of files, with the size of files. So it's really intended to scale to arbitrary large amount of data. And so the structure is we had a directory structure, then we have the SQLite files, and inside each SQLite file, we have multiple blobs, and the blobs are compressed DGGS UBJSON FG for vector data, or compressed DGGS UBJSON for raster. Both are basically DGGS quantized, but the difference is with the vector format, what happens is the vector are not rasterized, but each the coordinate pair of each point in the geometry is just replaced by a subzone index. This is the kind of thing that DGGAL can help you to resolve, convert back to a coordinate, for example. So you can see on the left, this is basically the DGGS UBJSON FG is an extension of OGC features and geometry JSON, which itself is an extension of GeoJSON. So you still have the whole OGC simple features geometry model. It's just the coordinates that are now quantized. Whereas for the DGGS UBJSON, what you have, the payload is essentially just the data values, and you imply from the position of those data values, you imply which subzone they map to. So both formats are very efficient, which is why we use it for this data store. And it's also one of the exchange format that OGC API DGGS can support. And we've implemented basically this set of tools first as a vibe coding experiment. That was really one of the primary goals. The other thing was to kind of illustrate how to use DGGAL in Python. So it's all open source. It's all in Python, easy to look at the source code. And also it's a full-fledged DGGS processing pipeline. So you can import raster or GeoJSON into DGGS. You can export it back to GeoJSON or a raster geotiff, for example, or you could serve the whole thing through OGC API DGGS, or you could fetch to clone from another DGGS API into a local data store. And finally, DGGFG is a conversion tool between GeoJSON and DGGS JSON FG. And this is some sample of what the server looks like, all the different endpoints, all the way from the landing page to the zone data requests. And another interesting thing is for the DGGS JSON, we support the custom depth and multiple depths as well. So it actually does the resampling, all kind of interesting things. Maybe very quickly, so H3 actually can be used for the OGC API DGGS, but there are some important things to keep in mind, and these are the things that we clarified in the pilot, and there's not a lot of awareness around this. Maybe we'll get a chance to talk a bit more about that tomorrow. But we made basically one contribution to the H3 project with the help of Joanna as well, who did the Java port about how to query the subzone. So you actually get exactly the zone inside the parent, not just based on the logical indexing. The second thing is you want to make sure that you really walk along these edges as opposed to just use the endpoint, because otherwise you're not going to get the right topological relationship between the different zone levels. And finally, what the actual coordinates are. According to the H3 documentation, it's spherical coordinates on the italic sphere, but most people probably use it as simply directly using the WGS84 coordinates. So there's a question about whether there should be a conversion from geodetic latitude to italic latitude when interfacing with the library. So those are some of the points we'll try to clarify in the ER. what are the next steps? So we want to support more grids. We want to
Jerome,
test
can you
more
wrap up fast?
Yeah, this is my
Yeah.
last slide. So we want to test the DGGAL high vibes more, improve the vector pipeline, and hope to support DGGS JSON FG in Gnosis Map Server. And also want to try to support CSCQL2 library for deriving fields and filtering, and also do some cross-collection queries and distributed multi-server analytics. So thank you very much. Yeah, and that's it. Sorry if I took too long.
No problem. Johan from Geomatis. So we're gonna delve into the client side, which is the AI pieces. So hopefully Kenichi will receive some of your answers, and we will get back to you soon.
Okay.
Messiah, yes. Yes,
Do
we
you
can
see
your
my
slides.
presentation? Okay.
Yes.
Okay, hello everyone. In the coming minutes, I'm going to present Examine Server with its new OGC DGGRS service and the different troubles and solutions we had in this pilot. So first, my name is Johan Thorel, and I'm working with Geomatis for 18 years. And I'm also OGC member. I'm a project manager, part of the project manager committee of the Apache SIS project, and manager of GeoToolkit and Examine software development kit. Briefly, the Geomatis company has been working in geospatial for about 20 years. It's also been involved in the OGC for as long. We're a kind of a small company with only 25 employees, but we have very high expertise in geospatial because we focus just on this topic. So we work mostly on Earth observation, planetology, defense, and environment in different standards, ISO, OGC, STANAG, AHO, and well, many different when it's needed. For this pilot, we have been working on the following open source project. You have the OGC Geo API, which is a programming interfaces for geospatial applications. We also work with Apache Spatial Information System, which we are developing most of it. We also work with GeoToolkit, which is a sandbox project for Apache SES. And Examine, which is the web server, which provides different OGC services for this pilot. What we plan to do with this pilot, we mostly focused on developing the server side here. So we had to first create Java APIs for discrete global grid reference systems. We also focused on implementing the service and passing conformance tests. So we had a service which is well, quite stable and matches what is expected. We ensured next what was if everything was working with the coverage and coordinate reference system APIs at the programming level, so that DGGRS fit in correctly, so we don't have any gaps or things which don't work as accorded. We also work into multi-dimensional data. So we tried to return as much as possible coverages with 2, 3, 4, or 5 dimensions, mixing both DGGRS and coordinate reference system for temporal, vertical axis, and so on. We also made a Java client. And last part, we ran a few benchmark and tests on the DGGRS services to compare the different solutions. The result we produced, which you can find in the final report, but here you have a quick list. So in part 11, you will have the description of our service. In Annex T, you will have the Geo API programming interfaces. In Annex U, we'll have the binding with DGGAL, A5, and all the other libraries. In Annex S, you have the special case of H3, which Jerome talked about a few minutes ago. In Annex H, you have DAR. In V, you have the benchmark. In W, you have a new prototype endpoint for the service. And in Annex X, you have the HIPS interoperability test. So the Examine server we have been working on has the following capabilities. We have 21 different DGGRS available. We have a large part of them which are coming from DGGAL library, but we also have A5, H3, LPIX, and S2, which are coming from different libraries. On the conformance side, we pass 20 out of 25 conformance classes. So we have all the mandatory ones and a few optional ones for different formats. We also support outputs in different formats. So you have JSON, UB, JSON, GeoJSON, GeoTIFF, NetCDF, DAR, and PNG. But of course, since we have a large backend, we can provide a lot of more format if needed. So since we developed a service, we don't have a lot of visuals available, but we have made an Explorer web interface for the participants to navigate in the different data available and see the different zones and statistics in the different DGGRS which we have. So here you can see 3 different DGGRS. You have H3, you have A5 and S2, which GeoTIFF, GeoPackage, and shapefile data. And all the data we are using on the server are processed on the fly by our service. So you don't need to resample or transform any of them. So it's kind of very fluent. Just add the data on the server and that's it. It's available. So nothing to transform here. So the first work we had to do was to analyze all the documents and all the libraries on DGGRS. So you have a few specifications, you have the testbed reports, you have different library, you have CDS, LPIX, DGGAL, A5, you have also HIPS, H3 geometry, S2 geometry. So it was kind of a lot of things to get in. And we started a very long process to create a programming API that fits everyone and fits the existing reference system API, which was already existing in OGC Geo API. So we plan on adding this new API in Apache SES first, and afterward we will propose it for the OGC Geo API standard working group. And the result of this work are 2 new packages, one for DGGRS and the other one for compound reference system to be able to mix DGGRS with temporal, vertical coordinate reference systems. So this is something new and no standard actually defines this case yet. After a few months, when participants started connecting their clients to server application, H3 was the first and only DGGRS in common. And quickly, first problem arose with this library. It lacked a determinist subzone function, which was needed to correctly implement the service. So at first, you can see the image at the bottom. We use the H3 library to get children recursively. So you have this snowflake shape, which is visible, and it's not what we want. So first attempt we made was to use the S2 geometry library to make intersections of the different zones on the globe. So this solution was a bit better, but as you can see, we had some extra zone outside the area we wanted. So it was still not a good solution. And in the end, we, with the help of the Thierry Jérôme, we rewrite a new subzone function. And as you can see, the new result is correct here. And as he said, we submitted to the H3 library, so it can be added, and so everyone can use it. An optional conformance class of the new service was about supporting the ZAR format. So okay, there is no problem with supporting this format, but there is a little something which was missing in the specification. There is no actual way to say how or encoded the geospatial information inside the ZAR. So we searched a little, and we explored the NetCDF CF convention and GeoZAR conventions, and we discovered that work was going on since 2023 to support HillPix in DGGRS, the HillPix DGGRS, sorry. Since they were very close to releasing it, we did not rush in to make them restart the work for all DGGRS. So instead, we started thinking on how to reuse what was done and extend it to fit the needs we had here for all DGGRS. So it resulted in a small set of new metadata attributes, which we can see here. Once everyone was starting to work, once everything was starting to work correctly with server and clients, some performance concerns started to come up. So after some optimization on the service, we decided to run a few benchmarks with two objectives. See if we have major differences between different DGGRS, and see if we could improve efficiency using different formats. So as you can see here on the left graph, you have the response time for each DGGRS on our service. And we can see that H3 is actually the slowest. S2 is the fastest. And well, if you can, the best choice would be to use EZA7H or EVA7H instead of H3 if it's available. In the right graph, you can see the response time of the server, the response size, sorry, by format. And actually, I didn't put the graph here, but all formats provide the same response time. So you're better off using the best compression. So UBJSON with gzip or CBOR if you have it, but the difference is minimal. What we concluded with those benchmarks is all DGGRS are able to provide a small size tile in less than a half second. And if you can use compression, of course, you should use it because it has literally no cost for the server. And of course, if you can also try to make queries with a lot of zones and not a lot of different queries with just a few zones each time. So it's better off to query a lot in just one request. So you will have more details in the annex in the engineering report. Another problem which was raised was the complexity of the DGGRS API. The API itself is correct, but it's quite hard for a newcomer or someone who doesn't have a DGGRS library at hand. So here in this example, we have a client which wants to download a specific area at a given resolution. So first he has to find all the parent zones which will be needed to retrieve the data. Then he has to ensure that he comply with the existing subzone, with the maximum subzone depths allowed by the server. He then have to make multiple requests to download everything. And then he has to remove duplicated zone and those outside the wanted area. So of course, all this can be done if you have a DGGRS library, but if you don't, it's quite complex. So the proposal here was a new endpoint, more friendly, and instead of working by zone IDs, you work using a geometry. So you give in a well-known text geometry, its coordinate reference system, and you ask zone depths you want or the zone accuracy you want, like for example 500 meters, and you have only what you requested back. So it doesn't have the so you get only what you asked for. It's more direct, we should say. So you don't need actually any knowledge in DGGRS to obtain something you can use quite simply behind. And this is a little off topic, but still interesting. In a side project, we had to work with data from the sky and other planets. And in fact, there is already a worldwide DGGRS service API which exists. It's called HIPS for a hierarchical progressive survey. And it serves data from worldwide space observation agencies, and everything is using the HELPIX DGGRS. So we wanted to see if we could forward all the exabytes of data which are already available with the OGC service here. So we made a small connector, and well, it works nicely. So I guess it's a good point for this new service here. Thank you for listening.
Okay, thank you, Johan, for a great presentation. All right, the next presentation, Craig CompuSalt.
Okay, can you hear me?
Yes, we can hear you very well.
Okay, perfectly. I'll give me a moment. I'll put my slides up. All right, are you able to see that? See my slides?
Full screen, yes. Go ahead.
Perfect. Sorry, just give me a moment. There we go. Okay. Oh, I'm sorry. Yeah. So I'm Craig Kaufman. I'm from CompuSalt. I'm a project engineer with the company now for over 30 years. I've done a lot of work with OGC projects in the past. I'll be talking about our AI-enabled DGGS client that we developed for this pilot. A little bit about our company. We operate out of Newfoundland. We're in Mount Pearl, which is just outside the capital, St. John's. We've got branch offices in Halifax, Ottawa. We have US and European subsidiaries as well. We've been around for over 40 years now, and we've done a lot of work in geospatial specifications, standards-based geospatial software, and so on. Just talking now about the client that we developed. So we put together an AI-enabled DGGS client, which is it's a chatbot client, and we had developed a chatbot for a prior project. So we took the what we learned from that and expanded it to include DGGS capabilities. So here's a screenshot just showing the client. We have a chat window on the left-hand side of the screen. We have a map on the right to visualize the results, and the user enters their prompt at the bottom, and we'll bring this up briefly a little later. Here's a little summary of the architecture that we were using for the client. We have a front-end client that's developed in React. The map is using open layers, and then we have 3 microservices behind the scenes serving as the main chat API, tools API for running external tools that reach out to a geocoder for name resolution and to the DGGS endpoints. And then we have the LLM API for the AI capabilities in the back. And then this is just a little summary of what the architecture works. Again, as I said, we developed the chatbot using React. We have using Meta's large language model on the back end, which is Olama, and those are just the components of the software. Some of the features, we've got the chat-based API that generates the requests to the DGGS on the back end via the tools API and renders those in the map view. We do zone queries, zone data queries. We've implemented data filtering with CQL2, and we'd overlay the responses from the data retrieval requests. Some examples there, which I've got some screenshots of a little later on as well. We're able to support the GeoJSON and GeoTIFF data responses can be rendered in the client, and we support several different grid systems as well. The testing that we did with this during this pilot was primarily with servers from Geomatis and Echere, which who just spoke. Here's a list of the DGGRSs that we're currently supporting: H3, Gnosis, Global Grid, the HealPix variants, and some of the others. Some of the types of queries that we support, we do some data retrieval where we request certain types of data over different areas, different times. We've also implemented some data discovery queries to identify what data is available to the client, and some sample filtering queries based on the data that's returned. So we can retrieve, say, areas that are above or below a certain elevation based on population or whatever data sets are involved. Future directions for this is some additional queries involving AI insights, data aggregation, so forth. And I've got a slide a little later on talking about that. When we're putting together the AI queries, some of the considerations were what data collections are involved, how many of them are we doing queries involving multiple collections, or just retrieving data from a single collection. Are we doing any filter attributes? Are we filtering just on the geospatial and temporal, or are we filtering on the actual data values that are coming back? And what's the actual data being displayed? Are we doing any transformation or analysis, or are we just displaying the raw data that comes back? I'll just do a very brief little demonstration. Time is short, so I don't think we have a lot to show here, but so here's the actual client itself. So you can see I've already preloaded with a prompt for time purposes. Show me an Apple mosaic imagery over Canada, Ontario. Here's the response from the chatbot, and then here's the representation of that data in the map. And we can see it covers this particular zone here, which is at level 8. As you zoom in, we can see it actually has the subzones. I believe this goes down to the individual zones here are level 12. And this is H3, but again, as I mentioned, we do have support for various other zones as well. There's some of the other examples that we ran during the pilot. Just some screenshots showing what they look like. Here's another NAPL imagery query. Here's one that retrieves some raw contour data. This is one that does an elevation query in southern Manitoba and displays the results from that. Here's another one that does some filtering based on elevation, and it only displays the subzones that match the criteria that we provided. Some of the next steps that we wanted to do is do some improvement on the the AI capabilities of our chatbot, do some aggregation of the data that's provided. For example, show me flood levels over the past 50 years, to add some intelligence to the response so it can do things like showing example, show population density for low-lying areas. The AI, of course, we need to determine what constitutes a low-lying area. Want to do some predictive analysis, AI insights, things like show flood risk, show projected areas that are at risk of flooding, and so forth. And then for usability, show some have some additional data refinement queries, so we could say show this information in greater detail, for instance. And that's the end. I went through fairly quick, but I know we're short for time.
Thank you, Craig. Unfortunately, we won't have time for today, most likely for questions. But if anybody has questions, please put them in the chat. We store them for tomorrow, or maybe after, if magically we will have some time. But let's move to GeoInsight. Zhao or Michael, any of you?
Yes, I'm here.
Yes.
I have an entire video of the presentation. Please give me a thumbs up if you hear it and if you can see it. Hello, everyone. My name is Michael Jendrike, and together with my co-founder, João Manuel, we will be showing you what GeoInsight has done in this OGC, AI, and DGGS pilot. I will be talking a little bit about the concept of DGGS and how it relates to GeoAI. We will give you a small insight into our architecture, demonstrate our API implementation, and showcase the website that we have built around it. At the end, I will give a bit of a future outlook. A discrete global grid system, to me, is a world model. It is a way to partition the surface of the Earth into zones of equal size in an hierarchical manner. It is flipping the layer-based, data-centric view on its head. It puts space first. These zones become little containers that you can fill with data. Data, for example, temperature, surface height, population density, and so on and so forth. If you aggregate and associate data with these zones, you end up with a very digestible format for AI. You essentially get a large table. A single index lookup, the zone IDs, allow you to associate data sets with these zones, different values like I mentioned before. You can then label zones in a way that you want them to. You have a phenomenon, you label the zones, and the AI can classify these or find zones that look and have a similar context in terms of data. What is essentially happening when you encode or decode into DGGS is the following. A coordinate pair gets associated with a zone ID. That zone ID is very crucial in the later on processing and analysis and data retrieval. In this part, we're focusing on the data retrieval and want to showcase a bit our architecture that we have built around the OGC DGGS API. At the beginning of the pilot, we made the decision to provide any grid for any data set and at any refinement level. What that means is that data essentially gets and needs to be transformed on the fly because we didn't want to store data by ourselves. That prompted an architecture that is capable of doing so. And one of the components that we realized that we need, as well as on the server side as well, and also on the client side, is a library that generates or allows us to generate the zones. You need the zones to quantize, so to do the zonal statistics, as well as to visualize later on in the web browser, for example. GeoPlagma in this context is important. GeoPlagma is an open source library written in Rust. It is making use of DGGAL, DGGrid, and H3, for example. We have about 10 contributors at the moment and bi-weekly meetings. Currently, we're developing our own grid, but other grids that are already existing will be added, like S2, A5, or our heel picks. If you're interested, you can check out the GitHub repository called GeoPlegma. Now let's jump into the OGC DGS API implementation, and I will go to the browser for this. At the DGS endpoint, you can see all the 11 grids that we are supporting. Some of the names are a bit long because I had to specify what implementation they are coming from, like DGGrid or DGGAL. H3 is also included here, and IGO7 is also coming from the DGGrid command line tool, essentially. There will be more information about each grid systems at the specific endpoint for that. You can then also retrieve zones, like for this DGG grid ICR3H. It is loading quite fast. It's calling a command line tool, and then you can explore this grid system at the zones endpoint. You can do the same for other grid systems as well. Here's an R-Tier9R. If you click on a zone, you get the zone ID here at the bottom left corner. Of course, that also works with IVS7H, which is kind of our preferred grid system, and I will continue with that one. At the pilot, we focused on Manitoba, but here's a bounding box query to roughly cover Canada. And of course, in the collections endpoint, we have a few data sets here. These RCM data sets I will use now to query as well. Just as a side note, we also implemented for some of the data sets the queryables endpoint that seemed to be very necessary for the clients, as they need to know what can they actually ask. Going back to the data set itself, it is very important, like I mentioned, to think in these zone and zone IDs. Here are the zones essentially covering this RCM data set. What you have and what you get here is parent zones. You can think of them as parent zones for your batch processing. Each of these zones, you would then request data at a relative depth to that or from that zone ID to get to the actual data. That endpoint for data always needs a parent zone ID. And you can include that ID here in the top after the zones, and then do /data, and you can retrieve it as a JSON representation, which is a very compact format, where you essentially get a long array of values that are ordered in the way that the subzones are ordered. A little bit more convenient if you want to immediately visualize that and don't have a DGGS aware client, you just get it as GeoJSON. You could then copy that over, that GeoJSON, into, for example, geojson.io. There you go. From this parent zone that I selected the data from, you can now click on each of these zones, these subzones, and get the values that have been quantized for this RCM data set. It's not visualized in color right now. You can pick and choose that later on in your application. But essentially, it's giving you the reflectance values of that radar image. So far about the OGC API DGS implementation that we have made. Let's go to a little bit more convenient way to explore or show possibilities what you can do with this API.
So yes, as Michael was saying, we built and created a site called DGGS.io where you can explore DGGS in a sense. You can test your own API if you have a DGGS API. We have our own here, and from there on you can see your collections and list your DGRSs. If you just want to see your DGRSs, your grids, you can choose the grid. Then the responses are always shown on this side, and then you can see it on a map. And this one is showing the zones here and showing the map here. This is this API is showing for this refinement level. This is the default refinement level. If you have another API here, it will show a different the refinement level. And then if you zoom in, it will update according to the zoom level and will increase the refinement level. You can also choose a zone if you want. Then it will basically show that information. If you want to see the collections, you can also see the collections. And I pick one collection from our API, which is a rather sat imagery. And then I list the grids. I choose a grid. I show the zones. And when I show the zones, it immediately restricts the bounding box. It's not global anymore. It's in this case, it's a Manitoba region. And then if we zoom in, it will update the grid and the refinement level, basically. If you want to see also our data and our data endpoint, we have some use cases on the website as well that you can explore. We have this use case in specific that measures basically the depth of the ocean, and from there on, basically, you can explore, and you can also use our calculator to generate insights that then will basically output values that then are represented on the map.
I want to take a brief moment to wrap this up now. I want to get back to this idea of having these zones as containers. I would call them spatial tokens. And one of the crucial bits, I think, for us is to be able to query across collections and queryables, so that we get all the context information that you need for a zone. And that will be our main focus, to look at the storage component in more detail. We are also questioning our own strategy that we had at the beginning to support any grid and any data set and any refinement level. Especially the part to support any grid is very cumbersome, and essentially you would need a lot of storage if you pre-process your data, or you do on-the-fly transformation, and that is, in our experience, slow. And even though we are using cloud-optimized geotiffs, it's not an ideal way. We will move to a persistent storage for one grid system alone. That's it for now. Thank you. And if you have questions, write them in the comments or in the chat, and I will answer them there. Thank you.
Thank you, Michael. Thank you, Joe. I think we can take a 5-minute break and come back. We are almost at the 1.5-hour mark. If you don't mind, be back in 5 minutes. So it would be 27 in my time. And it's 6:23 in my time. It's going to be 6:27. So, and then we can continue on the safe software presentation and the rest of the presentation. Thank you. Short 5-minute break. Okay, hope you had a short break. Let's continue with the next presentation, which is Safe Software. Dean, are you there?
Yeah, Dean here. Actually, I've got to make sure when I share, I include sound. All right. It's too quick. All right, so you're able to see my screen okay?
Yes.
All right. So, yeah, thanks everybody for joining us today. And I'm Dean Hintz from Safe Software. I'm also joined in this presentation by Dave Campanis from my team here at Safe. So we're going to talk about how we used FME's data virtualization platform to implement OGC DGGS API and some of the things that we learned from that process. So yeah, just a quick intro to SAFE, as well as a little bit of background on our support for open standards and a couple of relevant past pilots that sort of contributed to this one. And then we'll jump into, Dave will talk about data virtualization. Also, we were supported by Kalen on this pilot. And just a quick word about the FME platform. It's a data integration harmonization platform, no code, sort of data flow development environment. And you kind of author the workflows in form and then publish it, for services like REST APIs on Flow. And that's available also in the cloud. And I guess our whole kind of niche or unique value is being able to integrate across virtually almost any kind of geospatial data, many other data types, everything from CAD to GIS to remote sense data, point clouds, data cubes. And we've been a member of OGC for more than 20 years. We've been in the business of geospatial for more than 30 years, and we support more than 30 OGC open standards. So we think we're closely aligned with OGC in terms of our support for making data more accessible and interoperable, and essentially community-based open standards. We think that ultimately supports data democratization, automation, and governance and agility. So here are just some of the past pilots that we participated in. Disaster Pilot 21 involved flood risk, drought fire risk in 23, urban heat island effect last year, and flood risk this year. And then we just see some patterns here where disaster managers and planners can explore potential and future hazards or current hazards and evaluate the resilience of their systems, and also do things like downscale climate model outputs to see what the impacts are locally, and ultimately have automated impact workflows that can test a range of different scenarios. So, the key thing is, the past is no longer a predictor of the future. So we have to be able to incorporate things like climate model outputs. So that's something that we looked at in the last couple of years. Not to spend too much time on this, but the urban heat island effect, where you have artificial surfaces absorb more heat. And so what's interesting here about this kind of grid math is this is something that we could also do for DGGS. So in this particular case, we're computing absorption and cooling effects and doing the raster algebra to make an urban heat island index, so that you kind of have this climate resilience digital twin that can generate much more localized heat alerts. And this is a kind of a reference, the same study area for the Red River. So we kind of got started with this in the OGC, partnering with Manitoba and NRCan, government of Manitoba. So we looked at this in some detail back in 2021 for the Red River Basin. I just had a conference with the Red River Basin last week here in Manitoba. And so what was cool about this is that we had the folks at RSS Hydro and Dartmouth Flood Observatory generated a data cube of a flood model. And so we leveraged that in this pilot as well. So in that pilot, we kind of vectorized that in order to basically support an application for finding essentially finding how to pass, the shortest or recommended path between 2 points to avoid flooded areas. That was the app that we developed. But then we also use that same data set in this pilot. So it's just a different presentation of it. So the whole point in AI-DGGS is how can we provide a universally referenceable geolocation to support both spatial data integration as well as AI agents. And we felt that this would be a good way for us to evaluate how well we can support OGC APIs with FME's data virtualization platform, and also how can we ingest the range of different data types and publish them via DGGS, things like raster DEMs as well as climate data cubes, time series. And then ultimately, one of the goals was to support orchestrated AI workflows. We'll get more into that later with folks like Terraframe, but basically being able to integrate DGGS with other types of AI workflows. So Open API via DV, data virtualization, and then Dave will tell us a little bit more about that in terms of the DGGAL libraries that we wrapped up as FME functions and published those on our FME hub. So we have a DGS encoder, decoder, and indexer, so that allows us to convert data to and from DGS JSON encodings, and then publish those as a Open API, OGC API DGS service, and then support ties with Terraframe and Hardis. And this is just kind of where we fit in that architecture diagram that Sina showed us earlier. And so just a very high level architecture diagram here from our context for our component, bringing in geospatial data like DEMs, bringing in spatial temporal data. So we had temperature and precipitation data for climate forecasts and flood depths from that flood model from 2021. And then we quantize all that, load it into our DGS platform, and then serve that up to the various DGS clients. So as I mentioned, we have a high-res flood DEM for Manitoba, and then we have the 60-month time step NetCDF data cubes for RCP 4.5 sort of warming scenario, and then flood depths from the 2011 flood, modeled on a 90-day daily time step from March 1, 2011. And so that's all loaded into our DGS service. We have a backend PostGIS database and then data virtualization to support the API, and also SQL 2 support. And we'll do more on Terraframe in a minute. So just a quick summary, and then I'll hand it over to Dave. Basically, our data virtualization platform is a no-code approach for generating open APIs on FME Flow that publishes the power of any FME workflow. So those of you who are maybe have seen FME workflows, we can basically publish those via Open API. And in this particular case, to support DGGS. All right, so I'm just going to jump into Dave's component.
There are two key components to Safe Software's discrete global grid data server: the new data virtualization service in FME Flow, and the DGGAL Python module imported into FME form. Data virtualization allows you to serve any source data using a REST API. Data virtualization supports Open API standards as well as custom APIs. You can begin by importing an Open API specification. The endpoint is created for you, along with all their parameters. You can add a response to each endpoint, or create a workspace to produce a dynamic result. The created workspace and output features automatically defined for you. You just need to finish the workflow process. The Open API import is a starting point. You can adjust the endpoints and parameters to suit the needs of your particular. After finalizing your API, you can output a new OpenAI API specification to match, then use it in Swagger to create interactive online documentation. Now, inside the endpoint workspaces, we needed to implement the DGGS indices. To do this, we use the open source DGGAL Python module from Mashare. This module provides all the tools required to work with the DGGS indices. It also includes all of the various DGGS indexing schemes. We built several FME Hub transformers around the module. The DGGS indexer contains all the tools to create indices along with their parents and children. It will also provide the indices to fill an arbitrary polygon. The DGGS relator tests the relationship between different indices, so you can see if they are parent and child, or adjoining, etc. The DGGS JSON encoder groups raster values into index values and outputs to the DGGS JSON file format. The DGGS JSON decoder reads DGGS JSON files to create GIS-type geometry. These transformers can be found on the FME Hub webpage. The FME Hub also includes complete documentation for the transformers. Here we see the decoder used in a workspace. And here we see the output overlaid on a base map. The decoder can handle multiple resolutions in the same file. This is the encoder in action. And here we see the JSON file it outputs. The encoder currently only supports a single resolution.
All right, so just to kind of wrap up in the next couple minutes, this is the screenshot of our server from a browser, where you can see the API definition and the collections and some sample output. This is a web view of some of the zone query. And just a nod to Conterra, we kind of based our OGC API for DGGS loosely on their features template that's also available on the hub for OGC API features. And so, yeah, basically the configuration involved data extraction from these different data sources like raster DEM and climate model data cubes, as well as the flood model data cube, and quantizing raster and time series data into those zone values. And then we also support a range of DGS conversions via API parameters, and we implemented SQL2 queries to support data filtering. And yeah, I guess this is more or less a repeat of that information. So there is a basic use case, and TerraFrame, we'll hear from them next, so they'll go into more detail. The whole idea here is that you query for a particular flood extent, and you get back flood information from that, and then link that to, and TerraFrame links that to their spatial knowledge graph to look at downstream effects. So if you have impacted transportation networks or transmission line networks, then what are the downstream effects, or how does that affect that network? And then wrap that up in an LLM. So that's just a quick snapshot of that use case that TerraFrame will elaborate on. There's some links when you get the deck later. This is what we also implemented a live current flood level service, which is a simulated one to make it more interesting. So we basically take the 90-day time series, and based on the timestamp, every time you query it, you get sequentially a different value back. And yeah, there's the test client display. So this is looking at that live flood, current flood level greater than 1 meter, zoom level 10. And you can see that at the red point there, it's 1.98 meters is the flood depth at about this is zoom level 10, about 150 meter resolution. And this is TerraFrame's zone query, and then the impacts of that on the powered network. So just to wrap up, lessons learned, you know, we're able to take a diversity of data sources and integrate them into GGS and publish them. what we didn't really have time to get into is how to maybe integrate that with other types of references by zone. Things like ZAR and COG would be a potential for higher resolution outputs. Also, it'd be good to test more things like scalability and caching. And really, the scope of this pilot was quite wide. There's a huge range of things that we developed. So this is the starting point, but sort of like phase one. So I think we've made good progress on the core architecture, but there's more work that we can do to refine disaster applications and integrate with a wider variety of AI agents. So these are the questions. We can look at some of these tomorrow. And yeah, just to wrap up, I think DGS provides a very powerful, universally referenceable geolocation that can also both support data integration across different domains, as well as support AI queries and AI agents. I think there's good, the FME data virtualization platform really leverages the power of FME and the stability and scalability of FME, which is a proven platform over the last 30 years. And I think there's a lot of interesting potential for orchestrating AI workflows and linking multiple AIs with different disaster-related data sources published by DGGS. And I think we've demonstrated that we can apply DGS to integrated spatial data services and disaster risk assessment. But obviously, there's a lot more work that we can do there. Thank you.
Thank you, Dean. Let's move on to the next presentation. Nathan from TerraFrame, or Justin.
Hello, everyone. Can you hear me and see my screen?
Yes, I can hear you well and see your screen.
Excellent. Hello, everyone. My name is Nathan. I'm the CEO and founder of TerraFrame. Some background on our company. We are an open source geospatial software development company. Since 2010, we've been developing interoperability solutions and geospatial analytical solutions that highly leverage geo-ontologies. So our experience with geo-ontologies and spatial knowledge graphs goes way back. So for this project, we expanded upon some of our current work that was funded by the U.S. Army Corps of Engineers under the disaster response context. And also this work was funded through the CDRP 2024 pilot projects. So the goal is to create a solution that is open source and can leverage the geoinformatics data in spatial data infrastructures and make that available to be used by large language models to create an environment where people can ask ad hoc and on-demand questions because in a disaster response context, you don't have time per question to find the data and integrate the data by location. And so although this work has been funded in this context, I think there are much more broader implications for other verticals. And so it's been great working with the group here and also with Safe Software and GeoInsight. And through that process, we realized that the DGS really has a lot to offer in this context. So specifically, because DGS offers a common reference system, a client, an AI-enabled client, such as the one I'm going to demonstrate here shortly, can query for different types of data from different sources. And as long as those sources are leveraging the same reference system, they can automatically integrate by common geographies. So the zones represent the zone IDs, a geography in common that all the data that are quantized to can all line up. And so once you can get, and also this format seems to be very useful for providing a more up-to-date and current statistical and aggregated data. And then once a client has that, a client can then try to determine, okay, what is the impact of the whatever the event is that's represented in those DGS zones. In this case, it'll be flooding. So what areas are impacted? So you can do kind of a cross-reference between features, but more importantly, by using something called spatial knowledge graphs. This is where we have a pretty long and strong background. Is spatial knowledge graphs are a way of representing networks of geographical features. So the advantage of spatial knowledge graphs is they can allow you to model downstream impact, so that in a disaster scenario, you can understand not just the immediately impacted area, but what are the areas that are that could be disrupted, even areas that are outside of that impacted zone. So what is the disruption to transportation? What is the disruption to healthcare access? The idea is that through spatial knowledge graphs, which represent the semantic relationship between features, like I said, how can we discover that downstream impact several degrees of separation from the immediately impacted area to really understand that cumulative impact picture? So using agentic orchestration, we're able to combine the best of both worlds. And also through this pilot, we demonstrated that you can combine DGGS through agentic orchestration, not just the spatial knowledge graphs, but other types of abstractions for geographic data. And so how it works is when a user asks a question to the AI client, that the model then analyzes that question, and based on the tools that we've configured for that agent, it can identify from the text what is the area of interest, what area is the person talking about. If there is some ambiguity, can prompt the user to specify, because there are several areas that have the same name. And then it knows through the configuration when it should query a DGGS backend, which DGGS backend it should query, because you can have different servers providing different types of data. And then once it gets that data back, it can then do an analysis with the spatial knowledge graph to understand that cumulative impact picture. So I'm going a little fast here so we have time to squeeze in a live demo. And so the way you would operationalize this moving forward is, in addition to publishing data from different government industry ministries and the entities that comprise of your national spatial data infrastructure, in addition to publicizing data as DGGS, but you could also publish data as spatial knowledge graphs to get that best of both worlds picture. You can provide that sort of more real-time context to the AI client. And again, the idea is this should enable the client to give users the ability to ask ad hoc and on-demand type questions. So the more data sets you bring into the picture that are normalized by these common geographies, the more you'll be able to connect the dots across multiple domains. So having said that, I want to be respectful for time, but also squeeze in a live demo. Okay, can you guys see my map interface?
Yes.
Okay, so what we're looking at here is an open source application. It's a reference implementation. We're calling the GeoAI Kaleidoscope. It's actually a fork of the GeoAI Kaleidoscope that has support for DGGS. And so it's designed to be domain agnostic, and if it works for your purposes, great. But the idea is that if you want to create a more custom tailored user interface for your problem, then you could use this as a reference. So I've already asked the question, what data do you provide? And so it has awareness of all the DGGS servers that it has access to. And so I'm going to ask a more specific question concerning clarity on the flood data that's available. Yep, so we have some better information on what's available. Now I'm going to ask a very more specific question, and that is, show me the data for the flood level collection in Winnipeg on a certain date. And so what it's doing, it parsed the question and identified that there is a reference to an area of interest. And it says, well, we have actually awareness of two Winnipegs. Are you referring to the town or the beach? We're going to select the town. And now it's going to query the DGS backend. So here we have some data. Okay, now we want to understand what the impact might be. So I'm going to do a follow-up query That is, show me the impacted roads. And so we have implemented a road network in a spatial knowledge graph. And so now we can detect the overlap. So this is where through the agentic orchestration based on the context of my question, it not only knows what backend to query, but also what type of query am I generating. In this case, it's generating a GeoSparkle query. And it's important to point out that that the DGGS backends and also the spatial knowledge graph are serving as a RAG. And that minimizes the danger of hallucination, because all of the data that are involved in your answer comes ultimately from those data structures. The model is being used for natural language processing, and from that for code generation. So it's not manufacturing information itself. Now, what we have seen from a fault scenario standpoint is you can either generate invalid code, or maybe it generates code that answers a slightly different question. But the advantage there too is, even though we've rarely seen that, is you can always audit the answer. You have access to the graph. You have access to the DGGS APIs, so you can really have an understanding of where that answer came from. So I think in the interest of time, I'll keep it. I'll stop here. I can continue on this demo, showing the same kind of behavior for power infrastructure networks, but it's the same concept. Now, for those of you who are interested in the mechanics of how to get this working. Part of this is covered in a workshop that I did at the Phosphor-G North America conference. And so if you get a copy of my slide deck, there'll be a link to that workshop there. Thank you.
Thank you, Nathan. Lucio, do you want to go next?
Here I am. Wait a second. Can you see my screen? I hope so.
Yes.
Okay.
And it's full screen. Go ahead, please.
Okay, thank you. Sorry, Lucio Coleacomo, 4113 Engineering, old-fashioned coordinates of my hometown, not in DGGS. I will update in a while. I've just started this activity of consultancy last year. So before I was working in Capgemini for 27 years at the European Union Satellite Center. Common operating picture, as you have seen from the first slide of Sina, I am a little bit apart of this, but I was concentrating on what is the context, the scenario, how would be possible to transmit all this information. So that's my main objective, and was quite important to include in this stuff the identity, provenance, and trust, because all this information in emergency situation has to deal with the classification, with security, and a lot of other managing of special information, and mainly how to integrate with a local language model accessible to a retrieval augmented generation RAG. Possible solution from the beginning was to revise what was already available at OGC level. So I was concentrating on my effort on OWS context, a quite good standard that I think should be updated for the current situation we have in these days with the new technologies and new format and new things to apply, because it could be a good mechanism to transfer the common operating picture from one side to the other. The problem of the OWS context that at the time was dedicated to data and some WMS services, so we should update this to the new situation. For example, transferring a process that say how to transfer a scenario where we have a flooding event that is dynamic. And I found out that the DGGS is a good mechanism to simplify queries, and mainly the 3D queries, like in this case, that is a three-dimensional approach. So my idea was to have a COP as an orchestrator to transfer information, but also to activate, if necessary, process if the user are allowed to recreate this information on the user on the different actors' desks, and also to transfer trustable information. From the LLM RAG part, the idea was to put in place this simple approach with Oyama, ChromaDB, Longchain, and Gradius web interface to have access to a data set of documents available. I will explain later why this choice and how I did it. The AWS context as it is today, nice job, doing quite well is business, but should be, as I said, revised for what we need. What we need is at least this part of the information, like the type of emergency, the classification traceability, and the DGGS elements to better identify the area and or the volume we are interested in to transfer all the different services and data. But as I said before, this is a mechanism also for multi-actor information distribution, security aware, reproducibility through service reference, and the COP shall capture not just data snapshot, but also executable service chain. As my colleagues previously were highlighting, we need this kind of mechanism to be able to transfer this information from one side to the other and to different users with different technologies and means they have access. And as we identified during the project, artificial intelligence results are collateral information, and to my opinion, they're always pending for human validation, so we can use it to increase the information inside to be transferred to another entity. But again, there is a certain approach that I define later, how to have something more valid as information. This is just an example. As I said, any authorized, this is important, actor can reproduce the exact analytical results by executing the service chain with the specified parameter. This is a good statement, I think, because we need to include these kind of things in emergency and the other type of activity. As an orchestrator, as I said, we have different actors with different clearance accessing all this information. So we need a sort of orchestration layer that with task decomposition, agent discovery, and capability matching, security clearance, eventually, trust score calculation, this is an important point, and aggregation, result validation, and provenance tracking. The real end is to store this information, for example, in a stack item, use a smart certificate, and use the AWS context for services. I already said this, sorry for the repetition. But here is an example of a possible scenario of orchestration of information of a COP with inside the data and services and scores for artificial intelligence. I did a simple interface QGIS plugin to show this. Is available. The link is in 2 slides. Here you can see the pickup of the location, the possibility to apply zoom scale, to define with different DGGS CRS. There are 4 of them there. And also to use a polygon, and in the future I would like to put a volume in the DGS to create a DGGS grid for querying what is below. Here you have several layers. And in the lower part, you see COP metadata, small local language model that you can query with predefined ontology. This is a concept that is important. I think to have less perturbation from the artificial intelligence, the data or LLM that can provide quite dispersed, scattered information on a lot of items, is better to concentrate, my personal opinion, on small local language model with quite well-defined and databases of information, documents or whatever, and automatically extract data dictionary out of this, and out of this an ontology. This is the interface for the RAG, with the RAG to query this small local data set. Here the different DGRS. I was using in this interface, this plugin, the DGGGAL library provided by Isire. And first conclusion, so we need to revise the context for a dynamic behavior for managing COP. DGGS is quite good to define precisely the area of interest, so to support a better filtering for artificial intelligence result, local language model. Support the revision of working group to see how we can deal with this result of artificial intelligence to have something more valid. I added the IPT provenance and identity, and the one effect of this is that I created, is available always on the GitHub, a stack extension for COP available for revision to be revised and to be proposed for this scope. The stuff here is another big part, the small part, but quite important, dynamic ontology, as I said. So at the beginning, we have already classic static ontologies. I think we need something more flexible, like schema on read or things like that. Merge between large language model and graph database and small local language model to have something dynamically updated, that can be dynamically updated on the purpose of the specific problem to deal with. This can, in this way, we identify knowns versus whatever, creating hierarchies and discovering whatever it is, axiom and learning rules automatically. To prevent ontology drift, we need to have the human in the loop. And to do the versioning of the ontology like we are using for code. So these are important steps to have this stuff quite under control. And as I said, I can create redundant and nonsensical categories. Human in the loop can help in filtering this, and the ontology can be versioned so to have something more stable and that can support as a collateral information the COP or WS context in a better way as an orchestrator. And that's it. I hope to have managed to have done in time.
Okay, thank you, Lucio. That was fast and helpful. Okay, now we have some times for geolinks. So, Alex, are you on call?
I'm here, but
Yes.
Dick will do the presentation.
Okay, just please be fast as possible.
All right. Let's say that.
You see the presentations?
Yes, we can see it. Yes,
yeah,
and we can hear you.
Okay, yeah. Good morning, good days, everyone. Welcome to the presentations. I'm Tech, a PhD student from the Landscape and Geophotonics Lab of University of Tartu. We also have Alexander Akumok, which is one of my co-supervisors. Today, I'm going to present our work on PyDGGS API for the pilot project. PyDGGS API is an implementation of the OGC AI-DGGS standard to unify the discovery and access to various DGGRS dataset. This simplifies the workflow of the downstream applications. And our goals are to support different types of DGGRS along with different storage options. And more importantly, it should be easily extendable with new DGGRS implementation and storage options. We also focus on the visualization of DGGRS dataset via Common GIS API. With those objectives, I first introduced the high-level architecture of PyDGGS API. It is implemented in Python. Conceptually, it consists of three main components. First, we have the application layer to handle the API logic, and the components for DGGRS and storage in the form of abstract classes. So the application layer of PyDGGS API is implemented using Fast API. It is one of the mainstream API framework in Python, which is easy to code and feasible for changes. In order to support with different DGGRS and storage to work with the application layer, the design provided two abstract classes as a skeleton to interact with the API logic. In this way, any new DGGRS and storage implementations can be easily achieved by inheriting from those abstract classes. This design enables PyDGGS API to support various DGGRS with different DGGRS library. Currently, the implementations support 5 different DGGRS. First, we have the IGO7 DGGRS, which is has a hexagonal DGGS that conform to the OGC DGGS standard. The implementation utilized the DGGrid and DGGrid for Pi to support the operation on the DGGRS. And thanks to the DGGAL Python library, it extends the implementation with HuPEX, RHuPEX, and IPS7H DGGRS. Currently, we also support the UI-HuPEX3. Moving on to the storage assets, the implementations currently support 3 types of storage. First, we have the CatHouse DB, which acts as a conventional DB storage. In addition, the implementation support 2 types, 2 chunk-based storage, which is STAR and ParQuid. They are very popular in geoscience because of their assess performance. And we use XArray data tree to support aggregated multi-refinement level data sets in STAR format. To support data sort in ParQuid format, we utilize the DuckDB as the engine to assess the data source. Throughout the project, we work closely with Francis from Grid to improve the API usability and functionality. The pre-built Docker image enable easy deployment for end user to use the API in just a few steps. And also we also work closely and discuss on several when we are implementing several conformance classes such as the CTR filter, data filter, data subsetting, and also we discuss a lot on how to handle temporal and non-temporal corrections. And during the we have published several data sets during the project period. Here we demonstrate the DEM accumulations and scope data sets in IGO7 DGGRS at around 500 spatial resolutions. Those data are gathered using the API and further visualized using Lombok in Python. To make it more easily accessible to end user, the implementation support the Mapbox vector tiles for each collection completed. Here is a screen cap of using the vector tiles API with QGIS on the DEM collections. And for the future development, we are currently working on the improvement of SAR indexing for IGO7. We aim to provide efficient and compact index for large scale data. We will also go into the resampling of DGRS datasets on the fly to other DGRS to other types of DGRS. That allows a single DGRS dataset to support various DGRS without the need of conversion again. And thank you. That's all from my side. Thank you for your patience and participations here.
Okay, thank you, Dick. And let's move to Stelios.
Hello again.
Stelios, can you also be fast as much as possible?
I'll try. I'll try. Let me do that. Is it full screen now?
Yes.
Okay. Hello again. I'm Stelios Kontarinis. I'm a managing partner of Hartis, and I will present you the AI client as part of this pilot that we developed. I'll talk about a bit about us, the client architecture, the administrative and regional data that we worked upon, how we made the model, how we model the risk with a flat impact index, how we used machine learning and random forest integration, what we developed, the DGGS playground and an AI map chatbot. I will present some live demo if there is time, and I will tell you about one publication that we are working upon. So we are a 12 years company. Our mission is to deliver cutting-edge geospatial solutions focusing on maritime safety and environmental sustainability. We consider ourselves pioneers in hydrospatial technologies, emphasizing open science, for hydrography and nautical cartography, and our expertise on developing nautical charts, sailing guides, and environmental data products adhering to international standards. Our name comes from the Greek word chartis, which means chart, and embodies the essence of modern cartography, which is a synergy of science, aesthetics, and advanced technology aimed at modeling and communicating spatial information with precision and clarity. The team, it's me, Lukas, Thomas, and Vasilis. I'll not go more details. You will have the deck afterwards. We are members of OGC since 2023, and we have been engaged in several innovation pilots. The previous pilot that was relevant to this one, it's the CDRP 2025, that we created a generative AI-powered decision support tool for coastal resilience. Actually, it was the first try that we produced a map or several maps talking to an AI and producing an automated and dynamic coastal vulnerability index for an area of interest that the user just typed in. I'll continue the system architecture. Okay, this is a slide from the system design when we did the proposal, what we thought about. It's that we have a client that we will talk to the servers, two at least servers, but we will create and train an NML model based on ground truth data. And I'll show you that we worked on 2022 flood analysis in a while. And based on this ground truth data, we'll also create a flood impact index. That the idea is to get dynamic weather data every 6 hours and produce new risk levels. That did not happen, but it's a thing that we should do in the future, having a dynamic flood impacts index calculated based on the prediction of weather data as they come from. And the idea was to have some what-if scenarios in order the user to use and utilize the chatbot. In high level, it's a Django application with an LLM module. We don't have the cron scheduler, as I said. This thing can happen in the future. We have a spatial database, but also we have AI-DGGS servers that we are querying up to. There were challenges that we thought in the beginning about what we will do about the accuracy, what we will do about the uncertainty of the data, and what we will do about the hallucination. It's all these things that we try to tackle within the project. I think our deliverables are valuable for both users, standards, and developers. We have some ideas put in place here. This is the system diagram. The user in natural language goes to an interface which is based on Node.js and React. On the back end, it's a Django system that has an AI orchestrator, which is a Bedrock service that has been powered by a RAG, VectorDB, and Bendix, and there is a powerful MCP tool layer that does spatial tools, has spatial tools, and queries various services like the Examine, the GeoLinks, the FME servers, OpenStreetMap, and also the local PostGIS data. The AI orchestrator goes to the Bedrock through OpenRouter, which is an LLM API. We have used various LLMs there to test. This is another way of seeing it based on the layers. It's intelligent and data layer on where we get the information, the orchestration layer, or where how the information flows within the system, and the presentation layer, it's what the user sees. This is a more complex data flow. I will not go through that, but this is more details on how we have implemented the system. In order to understand what are the peculiarities of the area, we did some analysis of what the data are in the Manitoba area. We looked for the administrative polygons within the South Manitoba and also in Winnipeg. We understood the road network. where are the cities, the towns and villages, and what is mainly the risk zone buffers if we do a simple contouring on the area. Then we did a very thorough analysis. There are many slides that will come up. I will go very fast in order not to take much time, but it will be there for references with text that you can read afterwards and understand what we have done. We created a flood impact index that it has 3 components. It has a hazard component that it gets data from satellite data, from meteorological data, from soil data, and from DEM topography. There is an exposure layer that comes from related to the population, what the population will have there, and a vulnerability index that relates to land cover and any other infrastructure that can be vulnerable. And there is a synthesis out of all these factors, all these parameters, and we have an index that we call it Flood Impact Index. We initiated the analysis with RCM datasets on 4 RCM datasets on the flood that initiated on the April of 2022, from the 20th of April to the 10th of May. And we did inserted data as to understand what were the dynamics of that flood. Here we see how we inserted ERA 5 land data. We did some footprint analysis to see where the flood was during all these days. Again, similar analysis here. Also here with different coloring based on the dates where the flood was. Here also a GIF that shows how the flood progressed. We calculated topographic metrics like HANT, D8 flow accumulation. We inserted ERA 5 precipitation analysis during all these days. And we had also statistical analysis for the total daily precipitation. We had a temporal evolution of average of snow depth and snow albedo. Sorry for going fast, but you will have the deck afterwards and you can read the text that goes with every slide. We calculated the TWI, Topography Wetness Index, and we had at the end made a first flood impact index calculation that produces this map that provides us a reference and the ground truth of what the risks were in that area for the flood of 2022. We not aggregated, but we have then created a grid having all this data in every pixel. We worked on a resolution 8 and a resolution 9 mainly. And we did also some analysis based on what we see if we work on a raster, what we see if we work on a hexagon grid-based analysis, and try to understand what are the benefits either having raster or DGGS analysis. There is a visual impact here that you can see that DGGS analysis has some benefits. We have also thought about the aggregation of when a cell can be considered as flooded or not. What shall be the idea behind this? And we did some analysis there. We examined experiment on the performance, having resolution 8 and resolution 9 analysis of the risk. We did some comparison of the nested resolution 8 and resolution 9 hexagons, and when one is considered flooded and in resolution 8 and when it's considered flooded in resolution 9. Aggregation of meteorological data, ERA 5, also we have seen something similar. Total precipitation, a time series of total precipitation, land cover of Canada. Sorry for going fast, but you will have the deck afterwards. Another data set important for the vulnerability, it's the population for the exposure, it's the population, river aligned discharge and lake cover integration. And we touch upon integrating forecasted data through GeoMet OGC API surface observations. We faced several issues there that the data were quite sparse, but we managed to have some initial findings there. Having all this analysis, we created the training data in order to train our model based on this data that we talked about. We found the importance and the weights of training our model. The hand and them are the most important parameters that is the outcome of our analysis. And when we trained the model, we did a comparison between what we have seen from the satellite images and what we see from our model, and see that the results are quite accurate. And at the end, having this trained data, we can have a flat probability, flat risk probability in every cell that we are asking the server what can be the flat probability and what is the exposure in the population, for example. Okay, let's move on what we developed after all this analysis. In order to understand what the servers are providing as data, it helps us to do a playground. We call it DGGS playground, that we can have an interface where we can select different data sets, select different grids, different bounding boxes, or area of interest, and a cell width. Cell width means something that a user can understand, meaning that what is the square, the root square of a cell. It's, for example, now it's 10 kilometers. So the user can understand that what is 10 kilometers and what is the cell size that we will talk about. And it is an interface that you can run queries. You can have multiple queries and see the results on the interface, and have the capability to keep also the query that you are doing also on the URL, so you can somehow share the URL with your analysis that you have done. Okay, this is the user interface of our AI pilot. What is very important is to guardrail the LLM, and this mainly was done through the prompt that we provided to the LLM. And for example, here you can see if you ask the client what you are doing, I'm a flood risk analyst for Southern Manitoba, and there is a scenario that we told the LLM that you may follow. What is there are three phases. One is do risk analysis based on the machine learning model that we developed. Then do an impact assessment on roads, buildings, hospitals, etc., and then do some operational response. The interface has also some active suggestions on the bottom that changed based on the phase that the LLM understands that the user is. What tools do you have? These are the MCP tools that we have created for the pilot. There are tools for the risk analysis, tools for the impact assessment, and tools for the operational response. And this is an actual scenario that we ask for a risk assessment on Morris. We will do it live in a while if everything goes well. And then we asked about the impact assessment on roads and provided some information on what roads are impacted. This is a further analysis and with better data analysis. So we categorize the roads on severity, having different colors, red to green, based on the risk category. Okay, I will switch to live demo and let's see if everything goes well.
Stelios, we have only 1 minute to the meeting to be over, so just use 1 minute.
I'll try to do that. Okay, this is our interface. you see here there are active suggestions that you can ask the system on different area of interest. For example, the whole Red River Basin, Morris, St. John Baptist, which is an area near the river, and Emerson, which is down on the area of interest. I will try Morris, which is the most easiest one. There is some thinking that the system consulted by the prompt that we have provided on the back says, okay, I need to follow this protocol. I will do a risk analysis first. It asks me the users a risk analysis, so I will use the corresponding MCP tools. So the system provides some information on what is the responses from the MCP tool that does the risk assessment. This risk assessment has several parameters. It's the parameters, all the parameters I showed you before on how the ML model is calculating the risk. Three of them are shown here. This is the risk, the flood probability, but also we can see the hand, the DWI, the elevation, which is almost similar here. And there is always a hover information here with all these details. And then we will do what is the impact on the road segments. This will take half a minute if we have some time. I have initiated, okay, it says I have initiated this tool, the transportation impact analysis. Okay, it ran fast, okay, and it brought us the roads and the severity of the roads, the risk category, which shall be considered blocked, hazardous, colliery, or passable. Okay, I will stop here. I will come to the presentation. There are more 2 slides. Sorry for that. Okay. Okay, there is a mathematical analysis behind this. Vasilis from the team has done all this analysis, and we are preparing a paper for a scientific magazine in order to publish the work that we have done on this project. I thank you so much. Hope I was not very, yeah.
Thank you, Stelios. Yeah, so we are at the end of the hour, at the end of our meeting for today. So move the last 2 presentation to tomorrow early before the discussion panels. So we start with those 2 presentations, then we follow with the schedule for tomorrow. It will be great time for discussions tomorrow. So please bring your questions. The panels are open, and we are looking forward to your questions. And hopefully we will get some answers to those questions. And maybe it will bring more questions, which is even better. Thank you again, and hopefully see you all tomorrow. Thank you.